Hello, everybody, and welcome to your channel Thermal Engineering Concept and Principle. This is Professor Ali Tarrad. In this episode and series of different videos, we will talk about an application in the field of thermal engineering, which is the most important application in our heat transfer topic. What are the structural components of shell and tube bundle, heat exchangers, and how do they work? In this series, we will talk about this type of heat exchangers and how can we predict the thermal design of such heat exchangers. Dear friends and colleagues, we have presented uh, previously three videos about the thermal design of heat exchangers. We describe the structure of the shell and tube heat exchanger. We also presented the types of heat exchanger. What are the requirements to be prepared before commencing the design of heat exchanger, and we gave an sample, the practical study. In the present episode, we will continue the subject related to thermal design of heat exchangers. And in the present video, we will add some practical case studies to the previous examples, and the object um, is directed towards the application of the idea which has been presented in this subject, how to use these mathematical relations to design a heat engine. Let us go to the objectives. The main objectives of the present episode are related to the flow arrangement, and in fact, this section has been described before, but it has been repeated here just to enrich the information and to facilitate understanding the solution of the examples in the present episode. Uh, Additional practical case studies about the thermal design of heat exchanger, and then a summary of the content presented in the present episode. The fluid flow arrangement in the heat exchanger, and as we are talking about shell and tube heat exchanger, is the same for other types of heat exchangers. So there are two main types of fluid arrangement in the heat exchanger. The first one is called the counter flow pattern, and the second one is called the parallel flow pattern. In the first type, the fluids on the shell side and tube side entered the heat exchanger from opposite ends of the heat exchanger. Therefore, as they are passing through the heat exchanger, the flow is counter flow. And at the same time, when we talk about the other type, the fluids enter from the same end or the tube and shell sides, and they are leaving at the other end at the same direction. Therefore, these fluids, as they are passing through the heat exchanger, they are following a parallel path. So if we talk about the counterflow heat exchanger, if we have a look at the blue line, which represents the cold fluid, it enters at T sub Ci and leaves at T sub C naught. And when we have a look at the exit temperature, it will be there is a possibility to be higher than the exit temperature of the hot fluid. On the contrary, there is no possibility if we have a look on the right hand side um, graph, the cold fluid as it enters at T sub Ci, then it leaves at T sub C naught, which there is no possibility to be higher than the exit temperature. And in general, all the heat exchangers are preferred to have a counterflow. And in the counterflow, there is a uniform temperature distribution and they provide a good temperature difference between both fluids. So it is more efficient than the parallel flow pattern. Now let us consider a practical case study number 2. Here we have water at the rate of 50 kilogram per minute flows through a tube uh, and it is heated from 30 to 70 degrees Celsius by hot water enters the heat exchanger at 95 degrees centigrade and it loses energy. Then the temperature uh, at the exit drops to 75 degrees centigrade, and here we will take the overall heat transfer coefficient to be 280 watt per meter square degree centigrade. And here we have to mention in general that the overall heat transfer coefficient for a system or the heat exchanger composed of two fluids, water and oil, usually it is ranged between 100 and 350 watt per meter square degree centigrade. And this value falls within that range. And usually these values, of course, depend on the operating temperature and the type of oil as well. Then we need to calculate the heat transfer area for a double pipe, or we may consider the heat exchanger shell and tube with a single pass. And let us consider two cases where we have counterflow and parallel flow. Then we have some properties that is usually the heat capacity for oil and water, and we need to calculate the mass flow rate of oil to achieve uh, this process. Then the solution of this problem, we have both flows that is the counter flow and the parallel flow. Then let us start with the calculation of heating load. We have Q dot M dot Cp delta T of water. We have all these values. Then the total heat load will be 139.2 kilowatt. So the heat exchanger surface area. So we start with the counter flow arrangement, then we have delta T1 and delta T2 on both ends of the heat exchanger to be 25 degrees Celsius and 45 degrees Celsius. LMTD from the definition of the LMTD, then substitute these values for delta T1 and delta T2, then we will get LMTD to be 34.03 degrees Celsius. A note, which represents the total surface area of the heat exchanger, is equals to Q dot divided by U naught, delta T mean, and we have to mention that delta T mean for the single pass heat exchanger or double pipe is the same as LMTD because we have the temperature correction factor F sub T equal to 1. Then this relation will produce a surface area of 14.61 meters square for the counter flow arrangement. And for the parallel flow arrangement, we have delta T1 and delta T2 as calculated from the previous figures. Then we will get LMTD equal to 65 minus 5 divided by natural logarithm of 65 divided by 5. Then it will be 23.39 degrees Celsius. And the surface area as a result of these values will be 21.25 meters square. And it is clear that the surface area of the parallel flow arrangement will be higher than that of the uh, counter flow arrangement by a value of 31.3%. The second part, which is related to calculation of oil mass flow rate, we have m dot oil. This equation can be obtained from energy balance. And here we have the heat transfer rate um, lost by the oil is the same as the heat transfer rate absorbed by the water. And here we have assumed that the heat exchanger is well insulated and there is no heat loss to the ambient. From this equation, we may get m dot oil equal 3.762 kilogram per second. Practical case study number 3. Let us consider the information related to the operating conditions of case study number 1 in part 3 in the previous part. Um, and let us use those information in a shell and a tube heat exchanger with a single shell, and let us consider the heat exchanger is composed of two tube passes. Then what is the expected surface area of the heat exchanger to achieve the same heating load, and compare these results with those of single pass shell and tube exchanger. We have been stated that the heat capacity of water 4.175 kilojoule per kilogram Kelvin, and the specific heat of oil is equal to 1.83 kilojoule per kilogram Kelvin, and the overall heat transfer coefficient for the, the heat exchanger is 250 watt per meter square Kelvin. The solution of this um, problem is related to the two pass and single pass. Let's consider the two tube passes heat exchanger. Usually, the log mean temperature difference is based on considering counterflow with the correction factor for the two tube passes. Then we have the general form of delta T1 at the end, number 1, 90 minus 50 equal to 40 degrees Celsius, and delta T2 is equal to 30 degrees Celsius. The application of the relation for log mean temperature difference produces a value for the counterflow is equal to 34.76 degrees Celsius. And then we need to find the correction factor for the temperature from equation 4 and equation number 5, or using chart. So we have R equal 1.5 and S equal to 0.33. If we go and use this chart with these values, the intersection between R and S will give F sub t equal 0.91 and delta t mean equal F sub t times LMTD. We substitute the values of Ft and LMTD, then the mean temperature difference for this heat exchanger of the two tube passes will equal to 31.63 degrees Celsius. Continue with the calculation. Then the second step is to find the heating load of the heat exchanger. Q dot equal m dot Cp delta T. This is for water. And we have the flow rate 30 kilogram per minute. And we have Cp water and delta T water. Then the overall heating load equal to 41.75 kilowatt. And the surface area of the heat exchanger is equal to Q dot divided by U naught times delta T mean. If we substitute these values of Q dot, U naught, delta T mean, then the surface area will be 5.28 meters. As shown in this photo, this is a U-tube bundle heat exchanger, which in effect is the same as the two tube passes. And if we go to the second pass, single pass heat exchanger, as shown in this figure for the temperature distribution, we have F sub t equal to 1 for this heat exchanger, then delta T mean equal LMTD, and that means delta T mean equal to 34.76 degrees Celsius, and A naught in this effect will be equal to 4.8 meters square as a single tube pass heat exchanger. And here we have the single pass surface area less than the two pass heat exchanger, simply because we have a delta T mean for the single pass is higher than that of the two tube passes. This is how the calculation has been um, achieved, and this is the final solution for the single pass and two tube passes. And finally, dear friends, we have the summary. We have passed through the section which is related to the comparison of heat exchanger patterns, flow patterns, in fact, for the counter and parallel flow. And we have presented additional case studies for the design of gel and tube heat exchanger for a single and two tube passes. And we have some resources you may make an advantage of them. And you can find these references in a PDF with a link presented or seated in the description box. If you feel that uh, the content of the present video is useful, please share it and subscribe to the channel. And I will see you in near future with more practical cases or even more information on topic of heat transfer and energy. Bye bye.